All right, people. In our last lecture, we learned how to create our Stereonet and also how to put some measurements on there. In this lecture, we're going to learn a little bit more about Stereonets and also talk just briefly about block diagrams, which you're going to be asked to create as part of this lab. Okay, so we have two big topics that we got to cover and one small topic. The small topic is coordinate notations. You may not have been exposed to this, so we're going to go over it briefly. And then the big ones are stereonets and block diagrams. Okay, so coordinate notations. So you see here there are two different notations that any measurement can be written in. The first is azimuth notation, which we may be pretty familiar with, and the last video was created using. Okay, so we see this little strike and dip symbol here. Okay, and this is the azimuth 300 with a dip of 45 degrees to the northeast. We don't really care about the dip here though. Okay, what we really care about is the strike. Okay, so in azimuth notation, it is 300. In quadrant notation, the same measurement is north 60 west, and then the dip and dip direction are obviously the same. Okay, so the real difference is that the quadrants are divided into 4 different quadrants. And first you specify north or south. So there is the northwest quadrant and the northeast quadrant, and it is degrees east or west of north. Okay, so as you saw, it is north 60 west. Okay, so here's another one that you can try out. So our azimuth is 210 degrees. Okay, so the quadrant. So first we would specify whether it is north or south. And we see that 210 is in the southern quadrant. And then it is degrees east or west. So we see that 210 is 30 degrees west of south. So we would report this as south 30 west, and then a 30-degree northwest strike. So as I said, south 30 west, 30 degrees northwest strike. And you may be asked to convert in some of your lab materials this week. Another thing we should talk about briefly is plunge and trend. Okay, this describes the orientation of a line, something linear rather than planar. Okay, so strike and dip describes a plane, and we see it on a stereonet as a line. And then there is plunge and trend, which describes the orientation of a line, which we see on the stereonet as a point. Okay, so we write this the reverse of strike and dip, meaning that we write the plunge, which is equivalent to the dip, first, and then we write the trend, which is the azimuth or strike, second. And you notice that there is no dip direction here, and the reason for that is that the lineation plunges in the direction of the trend. Okay, so you don't need to specify a dip direction or a plunge direction because the plunge direction is baked into the trend measurement. Okay, so it is plunging in the direction that it trends, in other words. Okay, so by now you should have learned a little bit more about stereonets and their uses from the lecture, and you should have also created your stereonet along with the video before this. Okay, so a little bit about stereonets first is use and abuse, okay? So I call this the Great Circle Jungle, and I hope that none of you turn in stereonets that look like this because this is profoundly uninformative. It's not very clear what the person is trying to show here. And you can see that the strikes and the dips also sort of vary wildly. So I don't really particularly like this figure. So if your stereonets look like this, consider revising them. Unless they're practice, obviously. So the ones for this assignment will probably look something like this without as many points, but if you're asked to make a stereonet to do some structural analysis, try not to have them look like this. On the other hand, this is a series of nice looking stereonets. I took this photograph at the 2018 GSA convention, and the idea here is to use these stereonets to show that there's an angular unconformity between the Calendar Creek volcanics and the Oronto group sediments. Okay, so these stereonets here show the individual orientations in fainter lines, and then an average orientation in a bold line. And you can visually see from this figure that those two averages and the clouds of data that go with them are unequal, leading to the conclusion that you have an angular unconformity between those two units. Okay, so this is a good use of a stereonet. The previous slide was not a good use. The other thing that you see here are obviously clear labels and some information that helps put them in context. Okay, so why do we really care about stereonets? So they can be really useful, especially if you are in metamorphic terrains, if you want to determine fold orientations, or excuse me, fold axes. Fold axes are lineations, okay? So you can see in both of these figures, there's an axial plane that bisects the point where the two limbs of the fold meet, okay? And then running along the surface of this axial plane, or excuse, yes, running along the surface of the Earth along this axial plane is a fold axis. This fold axis itself is a lineation. Now, if the fold axis is not plunging, meaning that it doesn't have a plunge or that its plunge is 0, then your fold is not a plunging fold. It's just a syncline or an anticline. On the other hand, if your fold axis has some sort of plunge to it, then you can assume that you have a plunging syncline or anticline. So stereonets can be used for the purpose of finding the actual orientation of this fold axis. You can do this by finding the intersection of bedding planes on opposite limbs of a fold, right? So you could plot on a stereonet the limbs on the east side and the west side of this fold. Where those two planes intersect, or the average of those two planes intersect, you would have the fold axis. Similarly, if you measure the orientation of a cleavage in a rock and then one of the bedding surfaces, so you could be anywhere in the fold, right? You could just be on one limb, and if you see a sedimentary rock with cleavage in it, if you measure the cleavage and the bedding and then find the intersection of those, you've also found the fold axis. Finally, there's a method called the best fit girdle, but we're not going to deal with that, at least not yet. I may give you a chance to work with it in the future. Okay, so in this lab, you're going to be asked to recreate structures. I give you, a description of a structure, and you are meant to create a block diagram, which you're given a blank one of, that describes each of those structures. So here are two examples of what you may see in a completed block diagram, okay? So the top diagram here, and if we assume that north is in the direction, up away from this figure and away from us, then it would appear that we have a north plunging anticline. We know that it's an anticline, right, because they have this A shape, okay? On the bottom, on the other hand, we have a syncline. Okay, so this one, there's more of a V shape, okay? And so what this means is that, or what we see here is that this is not a plunging syncline, excuse me. So the top figure is a plunging anticline. The bottom figure does not have any plunge to it. And for your assignment, you will be asked to do one or the other, either a plunging syncline, a non-plunging, a plunging anticline, and there may be also some other instructions. So just a little review for you guys on fault types. Okay, so in your block diagram, some of them may be asking you to put some faults in them, okay? And you should show them in a similar way to this figure, okay? So you can see in this figure that they have drawn these beds that are ostensibly equivalent, right? So the gray bed is the same gray bed on either side of the footwall and the hanging wall, okay? And that allows you to visualize the sense of motion. And you should do the same thing on your figure, okay? So you should have maybe some indicator beds that are the same color on either side of the fault that then give an indication of what type of fault they are. Okay, and we see that on a normal fault, which means normal under the force of gravity, right, the hanging wall block has gone down. Okay, so this means that there's a fault separating them and the hanging wall goes down, and that you can see that offset. And that is generated by tensile forces, right? So there's stretching forces on the crust. That's what gives you normal faults. On the contrary, reverse faults show the opposite, right? They're the reverse of what you would expect under gravity, right? And that means that the hanging wall, which we can see here, has gone up, okay? And these are the result of compressive forces. So when you have crust that is squeezed and it is brittle, you will have reverse faulting. If the crust is ductile when you have compressive forces, then you get folding. And you can have you can have both in one package of rocks, right? If it was deformed when it was in its brittle stage, it would have faults, and then it can be further deformed in a ductile stage, giving folding, or in the opposite series of events. For your purposes right now, you won't need to worry about strike-slip faults, but it is good to know what those mean, and you can see that there's no vertical offset on those. It's a horizontal offset on a strike-slip fault. Okay, and so because some of you may not be familiar with dikes, you are asked to put dikes in one of your block diagram. A dike is a planar sheet-like magma body, and most times, or oftentimes, they're vertical. Okay, so basically you can imagine that, you know, rock fractures and then a sheet-like body of magma intrudes into the empty space that is left there. The resulting formation is a dike. Okay, so if you're asked to put a dike on your cross-section, this might be what you'd see along the side of one of those block diagrams. Okay. All right, everybody. I hope that's clear for you guys. That is the video lecture for this week. Should you have any questions, please come to the office hours. And I'll see you guys soon.